you want to be promoted to panelist, please raise your hand. And feel free to ask questions during the talk. Both speakers said it was okay. And I'm trying to encourage interaction in these days of remote visibility so that we actually talk to each other a little bit, even though we're on the computer. And if you want to ask questions, you can either just speak up, or maybe better is type into the chat window or the Q&A window, and I will intercept them and break into the talk as I feel fit. And if you're a panelist posting to the chat window, please change the default to be so that everything's visible to panelists and attendees so everyone can see the questions. And so let's get started then. So the first speaker is Irit Diener. She's a professor of computer science at the Weizmann Institute for Science. She's well known for her work in the theory of computer science, especially Pcp theorems and hardness of approximation. And without further ado, Irit, please go ahead. Oh, she's speaking. I don't have her title in front of me, but it's something about constraint satisfaction problems.
Yeah, I should have. Yeah, here it is. Constraint satisfaction and expansion. Sorry about that. Okay. Thank you very much, and thanks for the invitation. Okay, so I'm trying a new kind of medium for giving a talk, which is this OneNote. I'm not familiar with it, so let's see how it goes. Also, a disclaimer is that I prepared this talk especially for today, so maybe I omitted stuff, maybe I skipped some stuff. So please do ask me if anything is unclear. Please don't be shy. And let's start. Okay, so the topic that I chose is constraint satisfaction and expansion. So let's start by talking about constraint satisfaction problems. And really what we're going to be talking about is how does the expansion, or how does the structure, the graphical structure underlying constraint satisfaction problem, how does it affect how hard it is computationally? So instead of defining CSPs, let's look at a couple of examples. The most well-loved example is 3-set. Okay, so you have a bunch of Boolean variables x1 to xn, and you have a bunch of clauses. Each clause involves 3 variables, and they appear either as they are or in a negated form. And this is like the prototypical constraint satisfaction problem. Why is it called this way? Because you need to find an assignment to the variables so that all the clauses are satisfied. That is the problem here. And it's a constraint satisfaction problem because each clause, you can view it as a constraint. It's saying that among the variables x1, x2, and x3, there's all possible 8 assignments are allowed except for 1, which is, in this case, the 0, 0, 0 assignment. For the next clause, the assignment that's not allowed is the 0, 1, 0 assignment. So you always pick a triple of variables and disallow one of the 8 values. I mean, I'm sure we all know this, but I want to set the language so you know what I'm talking about. Another example of a CSP is the problem of graph coloring. In this problem, you are given not a formula, but rather a graph. And the goal is to assign the vertices with colors. So you're searching for an assignment of the vertices, a coloring. And this coloring, the constraints that it has is that the color of the ith vertex needs to be different from the color of the jth vertex whenever there's an edge between I and j. If there's no edge, there's no constraint. So every edge here is a constraint, and the constraint says the 2 endpoints need to be colored differently. Okay, so you can see that both of these are special cases of a more general kind of problem, which we call a CSP. You have Boolean variables. Actually, they don't have to be Boolean. I don't know why I wrote that. You have variables. In the coloring case, they're Q-ary. They get values in an alphabet of size Q. And you have a bunch of local constraints. In 3-set, these were the clauses. In the colorability, these were the edges. And each constraint looks at a constant number of variables, 3 or 2. And the goal is to find an assignment to all of the variables that satisfies all of the constraints. That's the satisfiability problem. We also look at a variant of this problem, which is an approximation variant or optimization, where instead of wanting to satisfy every single one of the constraints, we're interested in finding the assignment that maximizes, it satisfies as many as possible. There might be more than one. I shouldn't have said the, but we want to find some assignment that attains the maximal fraction of satisfiable constraints. And, why do we love these problems so much? They capture this mind-boggling phenomenon where locally the problem is really, really easy. Every constraint is over a constant number of bits. It's very easy to satisfy it separately. It's also easy maybe to satisfy a few of the constraints together, but once you try to satisfy all of them together, when you go global, everything, the picture changes, it becomes hard. And it's very interesting to understand what happens, how does this become hard? Okay. Okay, so this is the problem of CSP. And now I want to talk about the structure of the CSP. And later I'm going to try to say some words about how does the structure relate to the computational complexity. Okay, so what do I mean by structure? Okay, so I have this. So if I have a CSP, I can draw the following graph. It's called the factor graph. I'm looking only on the left side of the picture. So I have a bipartite graph. On one side, I put all the variables as nodes. And on the other side, I put all the constraints as nodes. And I connect the constraint to the variables that are constrained by it. And this is called the factor graph. And now this is already some kind of graphical depiction of my instance. And I can ask myself, how does the instance behave complexity-wise with respect to how it behaves graph theoretically, connectivity or expansion, and so on. Sometimes we don't like bipartite graphs so much. And so we look at the square of this graph. This is what I drew here on the bottom corner, where you put a graph only on the clauses and you connect a clause to another clause by going one step and then another step. So you go from a clause to a variable and then back to a clause. And whenever you took this step, you connect these two clauses. So you see here that C4 and C7 are connected in my two-step graph. So far, all I said is that if you give me a CSP, there's a natural graph I can look at. Actually, this is not the most natural thing to look at. There is something that I would argue is more natural, but we don't look at it so much. But let's talk about it just for a minute. And this is the, let's call it the constraint hypergraph. Okay, the constraint hypergraph. And this I would view as the most natural object. The constraint hypergraph has vertices for the variables. And for every constraint, if you want to constrain some collection of variables, then you would put a hyperedge on this set. Okay, so if you have a constraint is given by a set of vertices. Okay, here in 3-set, for example, this set has size 3, but it can have different sizes. And also, together with this set, you associate a little constraint function, which tells me which of the local assignments on this set alone are valid and which are invalid. So which ones I call satisfying and which ones I call unsatisfying. So this graph, together with these little functions, this is exactly just a different way to formulate a CSP. And the underlying graphical structure that you see here is a hypergraph. In the case of 3-set, it's a 3-uniform hypergraph. In the case of, I guess, okay. In the case of 3-set, it's a 3-uniform hypergraph. In the case of coloring, it's a 2-uniform, so it's actually a graph. So in the case of coloring, this description coincides with the graph that you're trying to color. This is another kind of reason or justification for me to say that I think this description, this graphical description, is like the correct way to describe the CSP. Okay. However, when the hypergraph is not a graph, when the arity of the constraints is more than 2, so they look at more than 2 variables, since we get a hypergraph, it is very hard to analyze. Algorithms don't really know what to do with a hypergraph. Okay, when we have a graph, we can look at the adjacency matrix, and we can do a bunch of linear algebra and spectral analysis on it, and these are very powerful tools. When we have a hypergraph, the tools that I know are always start by looking at some graph related to the hypergraph. Okay, and one of these graphs is the graph that we talked about just above, which is the graph where the vertices are the clauses, and you connect two clauses if they share a variable. Okay, another way of thinking about this graph, so we saw it just before by saying it's the two-step walk of the factor graph, moving from clause to variable to clause. Another way of viewing it is that you put all the clauses down as vertices, and then for every variable, you put a click connecting all the clauses that touch this variable. So this graph is really like a union of clicks. Okay, so this is a graph that sometimes we look at, but it's important to understand that the reason we look at this graph is not because it's a better description of our problem, but rather because it's a graph and we can analyze it much better than we can a hypergraph. Okay. So before I move on to talking about the hardness and what instances are hard and so on, I just want to say what is the kind of property that I will be most interested in when I study different structure of different instances, and this will be the property of graph expansion. So if you're given a graph with vertices V and edges E, we say that it's an edge expander if it has no bottleneck. So if you've never heard this definition before, which I doubt, but still, the way to think about this graph is that it's highly connected. No matter how you split the vertices into two parts, S and S complement, so this is a splitting of the vertices, there's going to be a lot of edges crossing between S and S complement. So if S is small, you expect the number of edges to be proportional to the size of S. I wrote here times D, assuming that this is, say, a D-regular graph. So this notion is especially interesting when the graph is sparse. When the graph is dense, it's also interesting, but then it's maybe less surprising that such graphs exist. It turns out that a random D-regular graph is a very good expander graph. And there are many other constructions of expander graphs, and this is not the topic of our talk. But I'm gonna, in the next 10-20 minutes, talk a lot about expanding graphs and expansion. And I want to emphasize that I'm talking at a kind of a high level. So there are many different definitions for expansion. There's this combinatorial definition of edge expansion. There are spectral definitions, and there's vertex expansion. And all of these are somewhat similar, but not exactly the same. And I'm not going to go into details exactly about these things. So let's just understand it to be some definition that says that the graph is very connected, robustly connected. Even if you remove some edges, it's still going to be connected. Okay. All right. So, so far, what we talked about was just generally CSPs, how to view them as graphs, and we defined what graph expansion is. Now let's talk about the hardness of 3-SAT, which we know it's NP complete. And we also know that it's not only NP hard to find a satisfying assignment exactly, it's also NP hard to find an approximately satisfying assignment. That's exactly the content of the Pcp theorem. And what does it say precisely? It says that the following problem is NP hard. Given a 3-SAT formula, an instance of 3-SAT, it's NP hard to decide. Oh, I see, there's something moved here. It's NP hard to decide if between option 1 and option 2. Option 1 is that this instance has value 1. And option 2 is that the value is bounded away from 1. It's 0.999 or less. And what is the value here? The value of an instance is something we mentioned earlier. It's the maximal fraction of constraints that are satisfiable. So you go over all possible assignments to the variables. Each assignment satisfies some of the clauses and doesn't satisfy some of them. So it has a value. It's a number between 0 and 1. And the value of the instance is the number that's the highest. So there's some assignment that attains the highest. There could be more than one such assignment, and this would be the value. And the question is, okay, you give me some formula. Do I know algorithmically to pinpoint the value or to approximate the value? So, okay, so the famous theorem says that deciding if the value is 1 or not 1, that's NP-hard. And the Pcp theorem that says that actually even there's a gap. So deciding if the value is 1 or below 0.999, that's also NP-hard. And in fact, you know, 0.999 is not even the right number for 3-sat. The right number is 7/8, which is also kind of interesting because every clause in itself has 7 out of the 8 possible assignments. So it means that a random assignment is as good as it gets. And I'm not going to go into this, but there's a huge amount of work trying to understand for different CSPs what is exactly the correct gap and so on. And we know a lot, but there's also a lot we don't know in there, but this is not going to be the topic of this talk. However, if you don't care so much about the exact gap, then the Pcp theorem tells you that for many, many different CSPs, for coloring, for 3-sat, and many other examples, you get some gap immediately because you can do some kind of gadget reduction between the two. So before I continue, I don't have a good sense of what the participants here know and so on. So if there's any questions or please ask me. I don't know if to take it that I'm going too slow or not, but okay. All right, so NP-hard instances, to start with, we don't know what they look like, but I want to talk a little bit about what kind of instances come out of the proof of the Pcp theorem. Okay, thanks. So to do that, I want to look a little bit at the proof of the Pcp theorem and see how the proof goes, and then we can look at the structure of the instances that come out. Because the proof of the Pcp theorem, what does it do? It's a reduction. So you start out with an instance you don't know anything about. It's an NP-hard instance. And then you encode it and change it, and you get a new instance where now you have a gap. So previously you only knew that either the value is 1 or it's not 1, and that's NP-hard. And after this algorithm that is part of the proof, you get a new instance that now has this gap. Either the value is 1 or it is much smaller, like 0.99. So there's 2 different proofs for this theorem. The first one, this is the proof, the original proof, is the algebraic proof. And what it does is it takes the instance, I drew it here in blue, and you embed it or you encode it in some algebraic space. Okay, and you embed it inside a low degree polynomial over some finite field vector space. And then you break it into pieces by looking at the restriction of this polynomial to various lines. Okay, so I'm just saying it in very high level. So basically, you encode your instance in a polynomial, and then you look at its restrictions to various lines. And then you need to do some more argumentation. And an important part of this argumentation is that you look at this graph where the vertices are the lines, all the different lines. So, you know, this line, this line, this line. And you connect 2 lines if they intersect. So these are lines in high dimensional space. They don't always intersect. And you rely on the expansion of this graph. So in some sense, expansion appears in this proof, but it's less visible. The expansion is much more visible in the second proof for the Pcp theorem, which is the combinatorial proof. So let me show you just in one slide where expansion appears there. It's somehow easier to see. So in that proof, you start out with an instance, it's even more convenient, instead of thinking of 3 sets, to think of coloring. So you start off with a graph that you know either it's perfectly colorable or not. In the case of not, it means that no matter how you color the vertices, there's going to be at least one edge that has the same color on both endpoints. And you slowly convert it into a different graph and then to a different graph, and repeat this until in the end you get a graph so that no matter how you color it, at least 1% of the edges will see the same color. So how do you do this conversion? So let's see one step. In one step, you take this graph, and now for every vertex, you look, see this vertex? You look not only at this vertex, but also at all of its neighbors, and you create a new big vertex for this whole neighborhood. Okay, and also for each one of these vertices and their neighbors, you create a bigger vertex whose value encodes the entire neighborhood. And now, since if you assume that this initial graph had some expansion in it, which we do by some kind of not easy tricks, then you see that the new graph is more connected. And if there was some problem, it kind of is people notice it even from further away. So somehow the problem gets amplified because of the expansion of the graph. So to summarize this, and then you kind of keep repeating, and every time you do this amplification step, you rely on the expansion, the edge expansion of the graph, to show that your gap grew larger. Okay, so what is the conclusion of this? The conclusion is that in this theorem, in these 2 different proofs, you see expansion inside the proof. Somehow expansion helps us in these proofs to amplify the hardness of an instance. So the instance we get at the end of this theorem, the instances that are hard to approximate, will always have some kind of expansion, as far as I know. Okay, I guess that's it for this one. Okay. So far we talked about worst case instances.
Irit, can I ask a question?
Please.
Yeah, it's been a long time since I've looked at your proof that you just were outlining on the previous page. And I was just wondering, can you remind me how big is the expansion that you start with before you start this procedure, the graph, the first graph G you start with? How big is it?
Okay, first of all, thank you for asking the question. Maybe other people will also feel comfortable to ask. So you start off with one graph G, and then you do some kind of amplification step, and you get a new graph G. And the way and you keep going like this, I guess logarithmically many times. And the way the proof is currently phrased, even the initial graph G is already an expander, But how is it an expander? In a trivial way, you take your graph G, which you don't know anything about, and you just take an expander off the shelf, and you just kind of add these edges. These are like free edges. They're not real constraints. They're like free constraints.
Okay, good.
And then slowly these constraints merge with the other constraints. So
good.
Yeah.
Okay. Yeah, good. That's what I was asking. Thank you.
Of course, just to comment, this proof is inspired and similar from both the zigzag construction of expanders, and even more from Reingold's proof of the SL equals L, where he starts with a graph and he slowly changes it so that in the end it becomes an expander. But he cannot do this silly trick of overlaying an expander. So it's possible that also in this proof you don't need to do this step. It just makes the proof easier. So, but there are these proofs where the expansion grows in a more moderate way. But anyway, okay. So now in this slide, I want to talk about. So I would love to be able to say there is some kind of scale or where I can put the non-expanding on one side, the very expanding on the other side, and I can understand the complexity as a function of the expansion. Of course, I don't really have such a beautiful picture, but let me just tell you what we know so far. So I don't know why I put this. This is not relevant. So far we know, we saw that the PCP instances, these are like NP-hard instances, are somewhat expanding. So if this scale talks about how expanding is your graph, starting from the most non-expanding and all the way to the very extremely expanding, I want to draw on the upper, on the top, the hard instances, and in the bottom, the easy instances. So we know that PCP instances are somewhere in the middle. And we also know, it's kind of trivial, that highly disconnected instances are easy, right? Like if each clause involves completely different variables, of course, it's easy to solve your 3-sat. And in general, if your instance consists of small connected components, you can solve each connected component, even in time that's exponential in the size of this component. So that's highly disconnected instances are very easy. It doesn't even have to be completely disconnected. As long as you can partition your graph into a lot of small parts and have few crossing edges, you'll be able to give a decent approximation to the value of this instance, and this will be easy. Okay, so that's kind of the simple things that we know. And what other instances do we know, and what do we know about their structure? So the next kind of instances I want to talk about are random instances. Okay, I'm sure, I think I saw that this lecture series had some lectures about this. So let's talk about random instances. So in the case of random instances, let's focus first on 3-sat. Okay, so in the case of random instances, what kind of hardness do you expect? So one kind of hardness is when you're given two distributions. So D no is a distribution of instances where I expect the algorithm to see the instances and say no, it's unsatisfiable. And DS is a distribution of instances where the algorithm is supposed to say yes, it's a satisfiable instance. And the instances that people look at are instances of random 3-sat and planted random 3-sat. So what are these? Just quickly, you have n variables and you start randomly selecting clauses. So you select a triple of variables and some literal pattern, so some string where you disallow this string on these variables, and you repeat. This will give you a random 3-sat, and there's a very important parameter, which is the density, the ratio of the number of clauses to the number of variables. This really determines the satisfiability of these instances. And what is the planted random 3-sat? It's a similar situation, but when you select a random clause, you first you plant some assignment, alpha, some string of n bits, which is going to be your satisfying assignment. And now whenever you select a random clause, you make sure that this clause doesn't disallow alpha. So you make sure that the negation pattern is random, but it's not allowed to be the pattern that alpha has. Basically, you select random clauses so that alpha remains a satisfying assignment. Okay, so you get these two distributions, and now there are various conjectures that say that it's hard to distinguish between these two distributions. Now let's talk about what we know in terms of hardness and easiness. So even though for a constant density, so for density above, I don't know, 4 or 5, 4.3, a random 3-sat is going to be unsatisfiable for all densities all the way up to square root n. So even if there's n to the 1.1 clauses or even n to the 1.49 clauses, we still don't know any way to distinguish between the planted and the non-planted distributions. Okay, so this is a hard problem. Okay, and I would like to say that these are random instances, so the underlying graph being a random graph is probably a very, very good expander. But let me put a little asterisk because we will see soon it's not exactly correct. So this was a 3-sat. We'll get back to it in a minute, but first so this was 3-sat, right? Now let me move to a similar CSP, which we talked about earlier, which is the coloring CSP. So we can look at a similar two distributions for coloring. The no distribution, which is when you just select a random graph. So in this case, let's select a random d-regular graph, G and D. This is the distribution of selecting a random d-regular graph. And the planted distribution is the same, but so here I drew this picture. You select a random graph. So these black edges, you see here, these black edges are the random edges. And then you select a random partition. This is the green lines. And then after you select this random partition, you make sure to delete all the edges inside each part. And you only leave the edges that cross between the parts. Okay, now you made this graph 3-colorable. Okay, so this is the planted distribution. Okay, so whereas the random distribution, you just select random edges and that's it. In the planted, you delete the edges from inside each color class. Okay, and now, again, you ask yourself, is this easy or is this hard? So unlike the case of 3-sat, it turns out that this is actually easy. So back in '94, Alon and Kahale gave a spectral algorithm to recover the partition, the planted partitioning or the planted coloring in this distribution. And as I said before, a very important parameter is the density. For 3-sat, the density needs to go all the way above square root n, meaning the number of clauses is n times square root n before distinguishing planted from random becomes easy. For coloring, already at some constant density, the Alon-Kahale algorithm works. Okay, so you see very, very different behavior between these two CSPs, which on some level I view them as very similar. There's a very simple gadget reduction from one to the other. So you might find this a bit surprising.
Excuse me, could you define planted random 3-sat again, please?
Sure. So you want to select a random 3-sat, but you want to make sure that some specific assignment, in this case, it's this alpha. You see here, I chose this alpha. I chose a string on n bits, which are my n variables, and I'm going to force that this assignment will be a satisfying assignment. So now I select the clauses, and every time I select the clause, I select the triple of variables, but I also need to select a literal pattern. Which of the 8 assignments is going to be disallowed? And I'm going to make sure that alpha is not disallowed. So whatever alpha says there will be okay.
Thanks.
So I think if you had to make up your distribution, probably this is what most of us would think about. And so these things I think are very similar, and yet they have different behavior. And I want to try to understand in the next few minutes why these are different. Any more questions?
So one question is that in the 3-sat planted distribution, it will be quite biased towards so the signs of the literals are going to be biased towards the satisfying assignment, no?
You know, you're right. I'm not an expert in this, and I think to avoid this, usually people look at like not all equal sats so that you avoid this bias issue. And
okay.
And then you're right. I don't want to like get into the details, and I'm not an expert on this, but thanks. Okay, so what is really going on here? So just to kind of go back to this thing here, this scale. So what we see here is that random coloring, I draw it in the easy case because it's easy. Okay, using spectral algorithm. And whereas random 3-sat is actually hard. Random 3-sat. It's hard, for example, if you get a random 3-sat to know if it's unusual or unsatisfiable. If it has some non-trivial satisfying assignment or not. Now, let me just tell you.
Irit, that's a question. I think you said this already, but just to confirm, random 3-set, do we have any conditional theorems about that it is hard, or is this just we don't know an algorithm?
Okay, so conditional theorems, no. Unless you're willing to say, if I assume that it's hard, then it's hard.
Okay.
But we do have concrete lower bounds of the form like SDP integrality gaps. So we know that this whole family of semi-definite programming algorithms cannot, I mean, they fail on random 3-set. So that's the best evidence that I know for the hardness of these things. So I want to say a couple of words on what is going on in this spectral algorithm, in this Alon Kahal algorithm. How does it manage to recover the planted 3 coloring that we saw here? And why can't you just take this algorithm and run it on the random 3-set? Okay. So what's going on is that when you look at this graph, this random graph, the way to look at a graph is often by looking at the adjacency matrix and looking at the spectral decomposition, looking at the eigenvectors of this graph. And since it is a random graph, except for the top eigenvalue, which will be 1, all the other eigenvalues, when you normalize, all the other eigenvalues will be 1 over or 2 over square root b, very small. Okay, this is for a random graph. But when you plant these colorings, suddenly higher eigenvalues will appear, and these are eigenvalues that correspond to eigenvectors where you put, like, say, 0 here, -1 here, and +1 here. It's not hard to check that. I mean, if this was a exactly balanced partition, this would be an eigenvalue of this graph. If it's not an exactly balanced partition, it's an approximate eigenvalue, and this is the content of their paper. But from these approximate, from that, when you look at the eigenvectors, you can kind of round them and recover the partition. This is what they do. Okay, so this looks like a very neat algorithm. Why not? Let's try to apply it to the graph underlying the random 3-set. Okay, so first of all, to which graph will we apply it? So hypergraph doesn't have any spectral theorem. I mean, I don't know how to convert a hypergraph. I can make it into a 3-dimensional tensor, but then I don't know how to decompose it spectrally. So I need to have a graph, and that's why we're going to look at the clause versus clause graph that we talked before. And we can do that.
Just to confirm, the coloring graphs are also expanding, right?
Yes, they're also expanding, but you see, because of this, you see this vector that I wrote 0, -1, +1. I mean, for people who are not used to spectral analysis, this doesn't look like a vector. But if you think of the vector V, V in -1, 0, +1 to the V. Okay, I guess I shouldn't call it V. Let's call it X. Okay, so I have a vector with if V is the vertex set with a coordinate for every vertex, and this vector I put -1 on all the vertices in this part, 0 on all the vertices in this part, and +1 on all the vertices in this part. Then this vector, if you multiply it by the adjacency matrix of the graph, you will see that it has a very high eigenvalue, like -0.5 or -1/3. I don't remember, but something that is very far from 0. So it's not a very good expander. Okay, it was a very good expander, but then you removed a bunch of edges, and this vector suddenly came, and it's an indication that this is not such a great expander anymore. Okay, so without okay, so since I'm okay, I want to say another couple of things. Then let me just say that how is the algorithm that works for random coloring going to fail for a random 3-set? And the reason is that random coloring a random coloring graph is much more expanding than a random 3-set. So if I look at the no instance, the graph that wasn't planted, then GNP is really just an expander, whereas the graph that comes out of the random 3-set is not as good as an expander as you would think, because it's made out of many cliques that are, you can think of as randomly placed, but each such clique is in some sense, so this set of vertices that is a clique, in some sense it's a set that expands, but it doesn't expand as much as possible because it has many of the edges stay inside the clique. So it's like a mediocre expander. It's not an excellent expander, it's a mediocre expander. And because it's mediocre expander, when you plant a satisfying assignment, which means you remove some edges, okay, so something does happen to the eigenvalue decomposition, but it's hidden by all of these cliques. All of these cliques also have this behavior that, you know, they don't expand so well. So we cannot use our spectral algorithm to imitate what Alon and Kahala did for the case of coloring. So this is more like an excuse for why we don't know how to run the algorithm in the case of 3-set. But what I told Sam before is that it's not only an excuse in the sense that all of these spectral algorithms are captured by these semi-definite programming hierarchies. And we know that random 3-set, we can actually prove rigorously that random 3-set instances fool all of these SDP hierarchies. So if you're gonna find an algorithm to solve or to do something non-trivial on random 3-set, you're going to have to step out of the SDP hierarchy framework. Okay, so
May
I
I
think
ask,
I'm kind of...
Excuse me. Due to the question of Albert, you said that you normally work with not all equal set. Is that more expanding a little bit than 3-set?
Is it more expanding than 3-set? So in terms of, okay, so thanks for the question. Let's see together. So the clause, variable clause graph, this graph that I'm talking about here, doesn't change because this graph doesn't reflect the entire instance. It just reflects which triples of variables are chosen. So it doesn't depend on the predicate. However, the label extended graph, which let me define it, it does change when you change the predicate. Okay, and in particular, it makes maybe it is more expanding. I don't know how to answer it, but it's still not sufficiently expanding. So the label extended. So okay, let me just say it. I guess, should I really wrap up, or what's the status of? Can't hear.
It's fine to keep going. Yeah, so we had some extra time at the end for questions, so it's fine to have them during your talk instead.
Okay, all right.
Yeah.
Just to think what. Okay, so I think we're good. So let me just say this. So in the case of 3-set or not all equal set or 3-lean, any other predicate, the graph where you just take, you take vertices, you put vertices for the clauses and you connect them if they share a variable. This is kind of the graph underlying the instance, but of course it doesn't show all the information. What does show all the information? It's a kind of a lift of this graph. We call it the label extended graph. In the label extended graph, let's look, for example, here. So you have a black vertex for every clause. This is like before, but now you replace this vertex by seven different new vertices for every one of the satisfying assignments for this clause. And here you have your 7 vertices for this clause. So for every clause you have 7 new vertices. And these vertices are labeled according to the clause. So here I wrote an example. So if the clause was x1 or x2 or x3, it means that the value 0, 0, 0 is disallowed. So the values are 0, 0, 1, 0, 0, 0, 1, 0, and so on. Okay? And the clause next to it, C2, they share a variable. This one has x1 and this one has x1. And in this clause, the value that's disallowed is 1, 0, 0. Okay, so I have all 4 assignments starting with 0, but the 1, 0, 0 here is not allowed. So again, I have 7 possible assignments. And then I'm going to put an edge whenever 2 assignments disagree. Okay, for example, this assignment wants to assign x1 the value 1, but this assignment wants to assign x1 the value 0. So they disagree. So I'm going to put an edge. So really what I have here is what I have here is all the assignments starting with a 0 conflict with all the assignments starting with a 1. So it's like 2 complete bipartite graphs like this. And I replace every pair of clauses by this graph. And this is the label extended graph. And on this graph, I should ask myself, it's a spectral behavior. However, the non-expansion of the graph that comes because you can look at all clauses containing a single variable is still going to be a problem, no matter if you have 3-sat or not all equal or 3-lin. So none of the spectral algorithms are expected to work in this case. I have to say, though, that there is some, in recent years, there is some work. Okay, but you can ask me later about it. Let me instead say some stuff that I plan to say. Okay. Okay. So the work of Alon Kahale that I mentioned about coloring was like a first work, as far as I know, doing this spectral analysis. And later, this kind of was understood better in the context of regularity limits. So, you know, for dense graphs, the regularity lemma tells you that you can think of the graph as having a few different components, and inside each component, all the vertices behave in the same way. So it makes the graph from an n-vertex graph into a constant number of component graph. And then you can solve the CSP quickly. And the interesting thing is that there started to be generalizations from dense. Dense means that you have almost n-squared edges. But it turns out that if the graph is an expander, it behaves like it is dense. So there are some algorithms that use this to solve 2 CSPs. When I say 2 CSP, I mean like coloring, where the CSP is really on pairs. Okay, and this gives some thread of algorithms. A different thread of algorithms that is connected also shows that CSPs are easy when the graph is an expander and something even slightly more refined than expander, something called low threshold rank. It means that you can split the graph into a few pieces, but not too many. And then each piece itself is an expander. And all of these works were about problems that have 2 variables, like coloring. Then, more recently, people started to think about CSPs where the triples have certain extra properties. So there is this property of splitable tuples. And it's a property that you wouldn't necessarily think about it a priori, because it's something like saying it's like a random 3-set, but it's even more expanding than random 3-set. And typically people would shy away from such a statement because we always think that random is the most expanding. But it turns out that here is a property that is more expanding than random. So let's look, imagine you have some 3-set and you put all the variables on one side and all the pairs of variables on the other side. I'm talking here only about pairs that participate in some clause. Okay, and now I'm going to put an edge whenever the union of this x1 and this pair e4, e3, I guess I wrote, I don't know, together make a clause. Okay, so you connect a variable to all the completions into a clause. In a random 3-set, this graph will be very bad because every pair of variables will only have one neighbor going to the left. if it's sparse enough. Once the three-set becomes dense, then the graph might be more connected. Anyway, an instance is splittable if this graph is expanding, and when this graph is expanding, you can again apply these techniques like the regularity lemma and get better algorithms. Okay, so this is my last.
Could you show the reference again, please?
The reference.
Okay, yeah, I got it. Thanks.
Okay, cool. Okay, so we talked already about the fact that random three-sat and random instances are hard for all the studied convex programming hierarchies, even the strongest ones, the sum of squares hierarchy. This was shown by Grigoriev. And these are for random three-sat. Recently, in a work, we showed different kind of instances coming from, I wrote here HDX based, but you should read it as splittable, or let me say related to splittable. I don't know how to say it. Those instances that previously we talked about and said that they're easy, very related instances coming from high-dimensional expanders, we showed that they are hard. So there is some very strange phenomenon going on over there, which I don't understand. In these high-dimensional expanders, this is a completely object that's relatively new. It's a very strange object, very non-random. It's an object that you construct from group theoretic ideas or number theoretic ideas. And it has this structure that it has very few triples, and yet they overlap in a very non-trivial way. So it's more expanding than a random three-set. And so on one hand, it's easy. On the other hand, it's hard. And in all of these proofs, you prove hardness using expansion, but these are different forms of expansion. So I don't know. It's a story without a nice conclusion. It's more like the beginning of a story, maybe. To conclude, let me say what we talked about CSPs and their structure. And we saw empirically that expansion occurs both in hardness proofs and in algorithms and in hardness SDP lower bounds. It's clear that too much expansion makes the instance easy. Too little expansion, when it's very disconnected, also makes the instance easy. So some mediocre expansion is where the hardness happens, it seems. Okay, but it's still a long way from understanding really what's going on. Okay, and in that I'll end.
Okay, good. Thank you for a very nice talk. Let me applaud on account on part of everybody. And we have time for some questions. So we had some questions during the talk, but I think we also have time for more questions. So please speak up with questions or post into the chat window. And must be some questions here. Let me see. Someone raised their hand. Michelle, you see. Michelle, you want to go ahead and speak? Somebody raised their hand. Is that a question?
Maybe I can ask a question while.
Oh, I need someone. Oh, it's an attendee. Okay. Let me see here. Oh, of course. Let me, that's good. Okay, now you're promoted to panelist and you'll have to rejoin, unfortunately. So, but you'll be back in a moment. While he's coming back, a very quick question. I don't want a long answer to this, but you mentioned something about Reingold's theorem. Is there any chance of a simpler proof of the Pcp theorem using his starting from? I mean, is there any interaction, I guess, between the two proofs? I'm trying to say here. Is there different proof of the theorem based on that's possible?
I think the gap amplification theorem is very parallel to his theorem in the way that slowly the gap gets amplified. Mm-hmm. Actually, my hope for a simpler PCP theorem is by using these crazy high-dimensional expander objects from number theory, but I wouldn't, they would be very nice or simple constructions, but then the analysis would definitely not be easy. But
Okay.
yeah.
All right. Okay. And so now I think Michael had a question, perhaps, or was yeah. Oh, Antonina has a question. At least, what is known about the non-deregular case? Question. Problems that have arbitrary degree graphs? Question.
Okay, great. Thanks. So yeah, so a lot of the theories also holds for non-deregular graphs. You need to, when you diagonalize the graph, you need to take care of the different degrees of the vertices. But as far as for, so this is more for algorithms, right? Like in many cases, your graph is input to you from some input, and you need to work even on a non-deregular case. When you use these things for hardness and for lower bounds, it's rare that you need a non-deregular graph. I guess when you select a graph at random from GNP, it will be automatically not deregular, but the degree distribution is very concentrated.
Okay. Good.
So if I may ask a question. So you told us this story about Alon and Cajale's algorithm, how it started with random instances, and then people started to see what is the pseudo-random properties that you need, that are enough to get your algorithm, right? So, and you also mentioned random 3-sat, and we had some talks about random 3-sat. And there the focus has also always been into studying the structure of the solution space. But they always do this thing on average. So it's really a random 3-sat. They analyze the structure of the solution space on average. So what is the typical solution? So the question is whether there's some work that extracts some pseudo-random properties that would have the same behavior. Like I would like to have, for example, a pseudo-random property of 3-sat instances that guarantees that the solution space has, I don't know, whatever they call it, condensation or scattering or whatever. So is there something like this?
Yeah, it's an excellent question. In particular, for example, if you want to use hardness of random 3-sat, say for cryptography or for some problem where you want to have a better understanding of the solution space and so on, like you want to be collision resistant. So even if I give you one solution, you need to not be able to find another solution or something like that. So you're asking, do we know of some other, so is the question, do we know of a deterministic constructions of instances with the same solution space behavior?
Yes.
That's an excellent question. I don't know. I guess, okay, the closest I can think of is in terms of codes. So if the constraints happen to be linear constraints, you can still study the entire thing. It will be an overdetermined system of linear equations, but still there could be like a random linear code where there is some subspace of solutions and all the rest are not. And there, I think also the statistical physics works hold, right? That they still have this condensation and so on. But since we also know of constructions of error correcting codes that are not random, maybe they also have. Okay, honestly, I've never thought about it. Maybe coding theorists have thought about it. It's a good thing to think about. Thanks for the question.
Thanks.
Yeah.
Okay. Good. We also have a question in the chat window from Emre Yolku. I could read it for you, Emre, if you wish, or you can speak up. Can you see the chat window, Irit?
Yeah, I can. Let's read it. This may be a bit unrelated. Okay, maybe everyone can read, so.
Okay, yeah. Well, let me just say it. This may be a bit unrelated to the talk, but are there techniques that rely on other graphs corresponding to CNF formulas? I'm specifically curious about the resolution graph where each clause is a vertex and there exists an edge between two vertices if their clauses can be resolved on a single variable. Could this graph be useful for proof complexity lower bounds? resolving two clauses corresponds to a graph minor-like operation on this graph.
Okay, this needs to be answered maybe by someone who knows proof complexity better than me. I know that the expansion is also used for resolution lower bounds, but I don't know if it's this graph that is the expanding one.
Right.
Yeah, no, it is again on the clause variable incidence graph in that case.
Right. Mm-hmm. Yeah. Definitely sounds like an interesting question.
Yeah.
Okay. All right. Well, maybe we're a little bit out of time here. So thank you again very much for a really delightful talk. And
Thank you.
getting a lot of hand clapping going on here. So good.
Thanks for the great questions. Thank you very much.
Yes.
Okay.
Yes. Thank you for being willing to speak. And we'll take a 3-minute break, strictly enforced, and start at 38 minutes past the hour. And give you a chance to stretch your legs if you need to, though. And Alistair will be speaking in just a couple minutes.
Okay, I apologize to Alistair. I cannot stay for the next hour. My kids are waiting, but bye, everyone.
No worries. Thanks for the talk.
Bye.